Okay, so thank you very much for listening. Today I will present this GNSS Ocean Reflection Project. In simple words, what we are doing in this project is to measure water levels and significant wave height using a standard geodetic antenna, GNSS antenna. I'm working with Bin Chao, Jennifer Haas, Michael Murphy, and Phoebe Hudson. So during my career as a coastal engineer and recently as a geophysicist, I realized about the lack of observational data at the coast. This is very important for our coastal studies, and this is especially important right now in which we are trying to understand the effect or the consequences of the climate change in coastal hazards. So therefore, we need more data. There is a relatively new technique called GNSS interferometric reflectometry, which uses GNSS antennas in order to measure water levels and significant wave height. There is, and what we aim is try to do a contribution to the great work other research groups have done in this technique. So what we are doing in this experiment or in this project is to test the technique in the PRAD scripts and trying to analyze also the sources of errors of this technique measuring water levels and significant wave height. And finally, try to optimize the technique in order to reduce the errors. So the theory behind this technique is very simple. Basically analyze one of the main observables of the GNSS antennas, which is the signal to noise radio signal or the SNR. The SNR typically increase for higher elevation angles of the satellite, but also what we can observe is the effect of the multipath. The multipath is basically the interference related with signals not coming directly to the antenna, but going to reflecting surfaces nearby. And therefore, we can have an interference with this signal coming from reflecting surfaces. So depending on the elevation angle of the satellite, sometimes we have a constructive interference and in other moments we have destructive interference. And if we observe a detrended SNR signal, what we can observe is those oscillations related with this change of the interference. So using the oscillation or the frequency of this oscillation, finally we can isolate for the and we can solve a geometric analysis in order to solve for what we define as the reflection height, which is the vertical distance from the antenna to the reflecting surface or the sea surface. And for this, there is a traditional and standard procedure in order to come up with that value of H. Okay, but before to do the analysis, the standard analysis, we have to take care of two aspects. First of all, we have to understand where we are measuring or the footprint of the analysis. And for that, we can just use the elevation angle of the satellite and a geometric analysis in order to find the places where we are measuring. And actually here you can see a picture of the script sphere and in colors the places where we are having the measurements related with different satellites. Also, a very important aspect is related with the range of elevation angle where we are having a coherent reflection. After some elevation angle, the reflection starts to be incoherent, and in those situations, we are not able to capture or to do the analysis of the interference. Therefore, we had to define a new criterion in this study where we are analyzing the noise of the SNR signal and the strength or the amplitude of this oscillation related with interference in order to define the range where we are having coherent reflection. And after defining that criterion, what we did was to use a very simple analysis using the frequency of oscillation of this detrended SNR signal and the geometric analysis in order to obtain values of the reflection height. We did it for 3 constellations, for GPS, GLONASS, and Galileo. And in this panel, and this top panel, you can observe a comparison between our reflection height or the water level derived from the reflection height and the measurements of a traditional tide gauge, a NOAA tide gauge at the same pier. And if we use the tide gauge record as a reference of the true water level, here we can compare the errors of the GNSS interferometric reflectometry technique, which have a standard deviation of around 16 centimeters, which is actually not so bad. Here, actually, you can see a close-up in 2 days, comparing the blue line, which is the tide gauge, with our measurements using the GNSS antenna, which is fairly good. Okay, but in order to get insight more about the errors of the technique, what we did was to take this time history of the error, and we perform a wavelet analysis of that time history. And after that, what we did was to do a comparison or a correlation analysis between the error we are obtaining with the technique and some candidates of sources of errors. We first analyzed a Doppler effect, which was identified by Christine Larson in 2013, which is related with an error in the determination of the reflection height because of the motion of the sea surface while we are doing the measurement. So if we have an accurate values, an accurate time history of the water level, we can finally correct for that Doppler effect related with the sea surface motion. After doing that, we did the correction, and what we discovered is actually we are still having important errors for this specific area. And what we discovered is that in places where we are having big errors, we are also having a very strong correlation with the significant wave height of the area, which was actually measured with a traditional instrument at the same pier, operated by CDIP in the pier. And what we can observe is that actually the waves or the wave field is also contributing with important errors to the technique. So this is a very important discovery and something we have to take care in the future. Also, as a third candidate for sources of error, we received some help from people doing important research in this area, in the area of trying to analyze what is the effect of the atmosphere perturbing and producing errors into our estimation of reflection height. And that is how we worked for a couple of weeks with Dalia Nicolaou, who was doing a very important research in this topic. And what we discovered is actually it's not affecting our measurements and in this case, but is contributing with important errors to the mean sea level. And that is something we have to take care in the future, for sure. Okay, because the errors in this wavelet analysis I showed you before, because the errors are related with high frequency, that is good news because actually allow us to determine long periods from the water level records or the reflection height records. And that is the case, for example, from the astronomical tides, which are always related with long periods. And what we could observe is actually we are having a quality very comparable to the analysis we can do, for example, with a traditional tide gauge record. And here we are doing a harmonic analysis, and from the harmonic analysis, we are trying to obtain the amplitude and the phase of the dominant constituent of the tides. And you can observe that the most dominant constituents, the first 7 constituents are very well captured by the GNSS interferometric reflectometry technique, comparable to the tide gauge. And also, we can observe here a comparison with the crosses with the official constituent reported by NOAA for this station. And we are having very good news in terms of astronomical tide analysis. However, our challenge also, or our objective is try to use this technique in order to measure other processes. For example, storm surge, or if we are lucky and we have a lot of satellite, also try to measure tsunami waves. For these cases, we think we still need more accuracy, more than 20 centimeters of the 16 centimeters I showed you before. Therefore, what we did was to try to gain more insight about the quality of the shape of this SNR signal, the detrended SNR signal, and try to see if we can get more information in order to improve the accuracy. And that is how we followed research from Neviskin and Larson and Strandberg, who have been doing a great job in order to improve the accuracy of this technique. And what we got discovered is that they are also working not only with the frequency of this oscillation, but also they are working with other properties. For example, the decay of the SNR signal when we are changing from coherent reflection to incoherent reflection, and also they are working with the phase of the signal. And what we could discover empirically is that actually, if we are fitting a sinusoidal function to this record, we can observe that the phase of that function has a very strong correlation with the error we are actually having in each of these measurements. And for example, just using one day in which we are having the GNSS antenna and a traditional instrument measuring water levels, what we can do is try to do a calibration or try to find this relation between the error and the phase of the signal. After determining that function, we can do then a correction in other days where we are not having a traditional instrument measuring water levels and only our GNSS antenna. And by doing that, we could discover that actually we can correct or we can reduce the error for about 16 centimeters we were having with the traditional technique to something about 8 centimeters. Therefore, we are reducing the error, and here you can see a comparison in the gray dots, the error we were having before the correction, and in color, the new errors, which are the half of those from before. So this is very good news. Okay. In terms of significant wave height, which is the second parameter we would like to measure, we discover, or we follow the studies from previous authors, Solar and Alonso Arroyo, who discovered that the elevation angle where we are transitioning from coherent reflection and incoherent reflection, that angle can actually be related with the roughness of the surface, and then that roughness of the surface can be related with the significant wave height. Those authors did analysis for very small wave, and here we took the advantage to measure and to test the methodology for waves as high as 2 meters. And the big surprise is that actually we are getting a very good accuracy. For this technique, again, we need a couple of days of calibration in order to get this function or the relation between the transition angle and the significant wave height. And by using 1 day, we can get estimation of the significant wave height for later days with a standard deviation error of 14 centimeters if we are comparing our significant wave height record with a traditional record, which is actually a wave gauge located at the same pier and operated by CDIP. Okay, moving forward, what we are doing now is try to test this technique for extreme events. What we did a couple of weeks ago, for example, was to compare and collect data from an existing geodetic station, in this case, Bermuda Island, where we have a geodetic antenna. And we used that technique in order to measure, for example, the storm surge of a hurricane. In this case, the storm surge of Hurricane Teddy. And what we could observe that after doing the correction using this relation between error and phase, what we could discover is actually we can get a very accurate measurement of the storm surge. This is very promising, and it was very good news. So despite of the atmospheric perturbation related with a hurricane, we are still obtaining a very nice storm surge measurement. Also, a few days ago, we were lucky because we had a very strong storm in Scripps with waves in the order of 3 meters. And what we could discover is that we know that the wave field is an important source of error. So therefore, what we did was to try to show the accuracy when we are having high waves. And what we discovered is actually we are having problems because the waves are very high, and actually we are having errors in water levels and wave heavy estimation, as you can see in this plot, but actually they are not so bad. So what we want to do in the future is further improve the methodology and try to see if we can even maximize or minimize the error when we are having these very extreme events, and try to find some general relation in order to be used in other places. So it's kind of bad news, but not so bad news. And we have the record in order to improve the technique. So in conclusion, in conclusion, we are having a very good technique and a very good accuracy with this new methodology in order to measure water levels and significant wave height, but still the take-home message is that we still need more research in order to further optimize and improve and reduce the error for very extreme conditions. So thank you very much.